Okay, let's walk through a very simple AI model. Now, don't worry about the detail or the code. You can easily look that up online, or we'll be obviously seeing this in greater detail in the labs. What I want you to think about is the structure of what is going on. That's the important part for this boot camp. If you want to dig deeper into the code, that's the dev boot camp on building superintelligence, or one of the other hands-on neural net building or AI modeling / API boot camps using ChatGPT and Bard and Hugging Face, etc., put on by others. And if pushed, even I'll do one or two of these. Now, there are lots of them available. You can get them anywhere. Here, we're just going to show a simplistic AI model. So let's step through a simple linear regression model using Python and some Python AI tools from a Python plugin called Scikit Learn. Now, there's lots of plugins available. We're just using this particular one because it suits our purpose. Linear regression is looking at past existing data relationships to determine a future prediction based on new data. For example, we do this in the stock market. We do it all over the place as humans. The formula can be anything that represents data, and in this case, a line slope, m, and a variable b, but it doesn't really matter. It's just a relationship between two contexts, or a stimuli and a response. Or given x, how do we get y? So I can predict y from x without knowing the slope or a specific variable, etc., etc. Now you can see the last point hints at data structure and abstraction that we will use and that we discussed earlier. What we're really doing is using training data to train the AI model to make predictions based on its learning the relationship between the data points and then applying that to any new data. If we succeed, the machine will be able to make accurate predictions or responses based on new data or stimuli. Stimuli and response is a key generalized foundation of general intelligence. In ChatGPT, you key in a question or a directive, that's a stimuli, and the machine provides a response based on its learning. Those are the weights in the weight matrix. So here we talk about one method for selecting and sculpting the appropriate data. Now, implementing AI is not magic. It requires work, like deciding what you want to solve or achieve, that's a goal, and selecting the data to do so. So it's a bit of a chicken and egg scenario. You can't choose the data unless you understand the goal, but you can't understand the goal without considering the data. Catch-22. This is just one method. Now in AI, there are lots of pre-existing data sets and repositories you can get your hands on, or you can use your own data, same diff. We talked about pre-processing and data cleaning earlier, and whatever data you use, remember the garbage in, garbage out thing. You need to make sure that data is as clean as you can get it without going overboard. You don't want to waste resources cleaning data. I mean, the idea behind these things is to get the AI to generalize and figure out the data itself, even when it's surrounded by garbage. The same holds true for choosing a goal. A poorly chosen goal will result in a defective AI and a waste of resources and dollars. So you have to be smart about data selection and prep as well as goal selection. Now this is a very important step. If you get it wrong, you will fail and have a defective AI. You will split an existing data set into parts. One part is training, or initial input data that the model uses to train. Another piece is a goal or a target output or something to measure error or measure to. And then once the training is complete and validated, the balance of the data or the test data is used to test what the model has learned. Once the model is released, new data or stimuli is run through it and monitored to adjust the system for the next iteration of new data. Select a goal, train, run the test data, run new data. It's pretty straightforward, pretty simple, same thing we humans do in school. Now this is where data prep is important. You don't want to test zombies against a flower model. You do want to select the right data to achieve the goal in order to train the AI such that when you throw garbage at it later on, it can pick out the correct relationships that you're looking for. So let's walk through the model. We'll go into more detail of some of this stuff further on and in the lab. So we'll import libraries or code and data, and scikit-learn in this case is a Python library of programs and data, etc., with specific tools for data analysis that we can just call from our own programs. Iris is a classification data set or matrix of flowers using, and we'll use a pandas data frame to see this. It's a simple matrix of data of flowers in rows and sepal length and width and petal length and width in columns. Now the goal is to classify a flower based on its sepal petal features and values. Train test split divides the data into training and testing samples, X being features and Y being target vector or labels, and X-train being a 2D input array. Now k-neighbors, as you can see up here, groups similar nearby data points using a distance or proximity correlation. You can think of this as data in an XY scatter plot and using proximity as a weight vector. So how far are these things away from each other and which section are they in? So accuracy score is an error measurement, tech for data labels or classification, to interpret the measurements. How well is the system doing? Now you could code these pieces individually, but why would you do that? Instead, you can just call an instance of this data set and initialize variables and data. And you can split that into train, test, target arrays to accomplish the goal. Now random state is just what they call a shuffling control seed to ensure there's consistency in the randomness of the splits for successive runs of the same model. That's just a consistency measure. We won't go into these details. So we will call or initialize an instance of the neighbor classifier model, KNN classifier. We will fit the k-nearest neighbor classifier model to the training data set. So we're going to take this model, we're going to fit it into this data set. We're going to find which data points are closer and by how much, or proximity, and the values that they hold. So each of these things will hold a value, such as a classification. You can think of this as plotting your data on a graph and then seeing the data of other nearby points for reference. Fit instigates the training of the system against the data set to identify similar groupings and data. In this case, the system learns the relationship between data and labels. So what we're doing is trying to determine the best data label or classification based on how other feature value combinations are labeled, especially the ones that are similar, i.e. our nearest neighbor. Now this is used to predict class labels for testing data and eventually for new input data. And this is the basic model of AI, or learn/predict. This particular code also calculates accuracy against target data and then prints that out. You can think of this as taking a stack of pictures and sorting them into similar piles, then looking at the description on the back of the picture to see how they are labeled to determine the label for any new picture that you see. Now here's what it looks like when I run the code, and this literally takes a half a second to download and run. It's not very interesting, but the bottom line is that when the model was trained and ran on the data, it was effectively perfectly accurate. Now we could now take out the test data and insert new data to see what the prediction actually is. Now this little snippet of code gives us a peek inside the data set. If we replace the test data set with new data, the machine will apply its learning to the new data and make a new prediction about what classification the new data fits in. It's pretty simple to comprehend. Now, we will look in far greater detail ahead and in the labs about how this is working step by step and how we move this to more advanced neural nets, including how they update their weights or backpropagate. I sincerely hope you have no anxiety about seeing a bit of calculus and math, etc., etc. If you are allergic to STEM, then I apologize in advance. Now note, you can think of the target as a neighbors grouping, and you can plot all data out on a scatter diagram, as we'll see in the labs, and then more quickly predict the class of the next data just by knowing the proximity to a quadrant and splitting up the test. In the code, you'll see why, and why is the goal that we're aiming for. So what are we doing in this model? Well, we'll load the data set. We'll split the data set into goal, training, and testing. We'll instantiate the model, fit the model to the data, or train the machine to identify patterns. We'll apply the training to the testing set and measure accuracy and adjust with more data or change parameters, etc., etc. If we were to change some of these parameters, like the percentage of training versus test, you'll see variance in the accuracy. As we make the training data larger, the accuracy increases, but as we know, it's less efficient. If we make the training data larger, then the accuracy increases. So if the test data is very small, like 20%, then yeah, the training data is going to be 80% of the data. It's going to be fairly accurate, but it's going to be costly to do that. And the accuracy change isn't going to be that much. We're maybe going to go from 1 to about 96%. So this is this question of how precise and accurate do we want to be. But we can alter that and we can produce a different output. We use the output of the model or the learning to make new predictions using new data. We train the model on data to learn something, a goal, and then we apply the knowledge to brand new data or new stimuli. In a full deep learning neural net, weights would be applied and updated, and the model run repeatedly to improve the learning. So there's a number of different ways to validate model performance, limited only by your own innovation and imagination. But we need these evaluations to allow us to change the model and improve its performance. In a neural net, we take the variance of a prediction to a goal and adjust the weights via backpropagation, and we'll see this again in detail further in the bootcamp. We also need evaluations to help comprehend what the data means to our goals and to optimization. For humans, we use visualizations like charts and graphs, and so do AI, but they don't see visual graphs yet. They see raw numbers behind the graph, the math, just raw numbers. However, soon they will be able to understand visually, and actually they already can perceive a graph and other visualization and instantly comprehend the math behind it. So that's how fast AI is advancing. This is one future use of advanced AI systems to audit other AI systems and us humans. So speaking of visualizations, on the left is an example of a confusion matrix or a quadrant matrix used to represent data like scatter plots into categories. Now we talked about the nearest neighbors, and this is how we humans would visualize nearest neighbors. where are we in the which quadrant are we in to get the label. On the right is a scatter plot with a mean applied. Now this represents a form of generalization that we humans use frequently and that is common in machine learning. The takeaway here is that data can be represented to an AI in a way that imparts cognition about relationships and patterns of real-world elements using math, which we will see again in more detail later on. There's a brief comment about hyperparameters. Hyperparameters give us control over the models, such as random state and test size in the previous example. Now, these may not necessarily strictly fit the exact definition of a hyperparameter, as AI devs would call them today when building large neural nets, but they function similar in that they give you a control over the machine, the data, and the way it solves for a goal. But you can comprehend the idea of broad parameters called hyperparameters. The hyper comes from the extensive impact they have on large models. We use hyperparameters to tune the models. That's their function. At the advanced end of AI, these include the depth or layers of networks, size of data set components, run rates, optimization factors, etc., etc., etc. And in advanced general AI systems, we use such things as bias offsets, anomalous recognition, tuning, the persistence of attention, etc., etc. Most are just simple parameters, but newer systems use additional weight layers, such as attenuation weight layers. Now next we'll look a bit at how to deploy models, and then we'll take a break from the code tech and talk about the future, just in general. And then we'll return to more technical discussions a bit later.